This is Lynn Kaminsky again, and I'm very pleased to introduce Jesse Nelson, who has been working with me all year, even though I haven't actually yet met him in person. So one of the interesting things about this COVID year that we've just been through, and in fact, until recently, I didn't even know what he looked like because he didn't have a web camera on his computer. But we've spent a lot of time together on Zoom since we started this project. And Jesse did a great job. He really originated the whole method that we're using based on an old activity that I had that was on cards. It's now on the computer. And this is going to be a very important part of a future class for high school students. So I am very pleased to introduce Jesse Nelson, who will tell you about our multi-messenger astronomy masterclass. Take it away, Jesse.
I'm not hearing you, Jesse. I don't know if anyone else is not, but
microphone is muted. Sorry, starting over. Good afternoon, everybody. My name is Jesse Nelson. I've been working with Dr. Lynn Kaminsky on a multi-messenger astronomy masterclass. A masterclass is essentially a course that's designed to offer high school students a research-like experience and to teach them how to think like scientists. And this effort is sponsored in part by iGrav, which is an international gravitational wave education public outreach program. And the collaboration includes astronomers who are working on a variety of different fields, including gravitational waves and the electromagnetic spectrum. And the masterclass is intended to be a 3-day course, and my project in particular is focused on contributing the gamma ray astronomy portion of the course. And to that end, I've developed an online activity that I'll show you in a little bit. But before we get into all the details, let's define some of the terms that we'll be using. So to begin with, what is the electromagnetic spectrum? Basically, it's light. Most people are familiar with the visible portion of the electromagnetic spectrum because it's associated with the rainbow of colors that our eyes can see and interpret. Early astronomy was also based on visible light because it was just people looking up at the sky and trying to interpret what it was that they were seeing. But the visible portion of the electromagnetic spectrum is actually just a very narrow band of the full electromagnetic spectrum. We have less energetic forms of light like infrared, microwaves, radio waves, and more energetic forms of light, including ultraviolet rays, X-rays, and gamma rays. And like I said earlier, my activity is focusing on the gamma ray portion of the electromagnetic spectrum. And just to give a sense of scale, gamma rays can be, in excess of millions of times more energetic than visible light waves. And so as, technology progressed, we were able to, we were able to analyze the data that was coming to us through the cosmos in the full electromagnetic spectrum. And every time we added, a new channel of information, we gained a more complete understanding of what it was that we were looking at. And multi-messenger astronomy builds off of that same concept where, in this case, we're talking each new channel of information is referred to as a messenger because it's basically some wave or particle that carries information from the source, which is, some arbitrary cosmic process to us where we can interpret that data. So that includes things like the full electromagnetic spectrum, includes like cosmic rays, neutrinos, and gravitational waves. And the particular example that this course is based off of is the detection of a binary neutron star merger in 2017 using multiple messengers, in this case, gravitational waves and gamma rays. Here we just have a couple of different plots that show the merger, or what we interpret to be the merger happening. We have the LIGO data, which is basically just a plot of the frequency of the gravitational waves over time leading up to the merger. Essentially, just to give a brief rundown of what we're talking about when we talk about gravitational waves, if you take matter essentially curves space-time. If you compact a lot of matter into a relatively small spot, that it creates a very extreme curvature of space-time in that local area. If you take a couple of those objects and you spin them around each other, then you have some periodicity to that, changing space-time, and that can propagate out as gravitational waves. And as those gravitational waves leave the system, they're carrying energy with them. That system loses energy, the orbit becomes unstable. Those stars, those neutron stars, spiral inwards toward each other until they eventually merge. So that's this rising frequency that you're seeing up until the merger. And the Fermi and integral data, these are basically space-based gamma ray observatories. You see the corresponding peak here, which is just the gamma ray burst detection that's associated with the same event. And you also notice that there's a time delay between the two, which can actually convey one of the advantages of multi-messenger astronomy. Because, like I said earlier, astronomy was traditionally done in light, and light interacts with matter. And in this particular case, you have a lot of matter in that system when the two neutron stars are merging together. And when that event happens, the light has to, propagate outwards can propagate through that system before it can leave out into space and arrive at us. And that's what's causing this little time delay here. So by further developing, gravitational wave detectors, we can, we can point our optical sensors or basically all of our light sensors in that region of the sky and try to get earlier data on some of these events. And I have a clip that'll basically show you the same event happening. It's a sonification of the LIGO data. So this frequency of gravitational waves have been converted into sound waves that you'll hear, and you'll notice a rise in pitch as the two neutron stars, in spiral towards each other, and then it'll culminate in a little peak at the end of the chirp, which is the actual merger event. And then a couple of seconds later, you'll hear a little bell that corresponds to the gamma ray burst detection from Fermi. So here is the little clip real quick. This is the rising pitch that you hear from LIGO as the neutron stars get closer and closer. There's the merger, and there's the gamma ray burst. All right, so what are gamma ray bursts? Basically, gamma ray bursts are the most energetic processes that are known to occur in the present day universe, but not all gamma ray bursts originate, from the same mechanism. We have our activity focuses on 3 different types of gamma ray bursts. We include short gamma ray bursts, which are similar to what we just saw there. Those are basically resulting from binary pairs of neutron stars or black holes or any combination of those two merging into each other, and they're called short gamma ray bursts because that process is relatively quick. It evolves over a period of less than about 2 seconds. There are long gamma ray bursts, which basically result from core collapse supernovae. That process just takes a little bit longer. The gamma ray bursts, that evolves over a longer period of time, maybe tens of seconds up to like maybe more than a minute. And then we have soft gamma repeaters, which basically those are disruptions in the surfaces of magnetars, which result from shifting magnetic fields. A magnetar is basically just a neutron star that has an exceptionally intense magnetic field. So when those fields shift, it can accelerate, charged particles out at, very high speeds and just spew out a bunch of gamma rays. And since unlike the previous 2 processes, which actually meaningfully, either destroy or transform what it was that created the gamma ray burst, this process is repeatable, thus soft gamma repeater, because that doesn't actually destroy the magnetar. It's just a change in its magnetic field that spews out some particles and highly energetic photons, and that can happen over and over again. So that's why those objects are known to repeat themselves. Anyway, we have data on 15 different gamma ray bursts, and we're tasking students with categorizing them based on their shared characteristics without necessarily having advanced information about those 3 categories I just told you about. So it's basically, this is that research-like experience where we just give them the data and we ask them to develop their own systems of categories that, for how to group each of those different types of gamma ray bursts. Ideally, they'll come up with a same system or something similar, but we'll get into that in a little bit. This is an example of one of the cards that we give them with all the information on some of the 15 different gamma ray bursts. At the top, we have the name of the gamma ray burst that we've made based on its position in the equatorial coordinate system, and that's basically explained by this little diagram here. We have basically, this is just the position of the object in the sky. You basically you project the equator of the Earth onto the celestial sphere or the sky, and then you have an angle called right ascension, which is basically your position around that plane, and it's given in sidereal hours, minutes, and seconds. So it's a 24-hour for a full revolution around the circle. So in this particular case, it's 12 hours, 32 minutes. So it's a little more than halfway around the circle. And then you have declination, which is just your angle above or below that plane. So in this case, -11, that's in degrees. So we're basically a little bit more than halfway around the circle and then a little bit under the plane by 11 degrees. And we also give the burst location in galactic coordinates, which is just another, it's a similar coordinate system. It's just using a different frame of reference. In this case, we basically project a plane from the sun to the center of the galaxy. And then you have galactic longitude around that plane, and then galactic latitude above or below that plane. And other than the fact that these are both given in degrees, it's basically the same system, just with a different frame of reference, as I said. In the middle, you have a light curve associated with the gamma ray burst. And basically this just plots how the intensity of the event evolved over time. We also tell them the energy peak associated with each burst, which is basically the energy level at which the greatest number of photons from the event was associated with. We tell them whether or not the burst was known to repeat, or whether the object associated with the burst was known to, basically spew off gamma ray bursts multiple times. In this case, it didn't. We also tell them whether or not the object is has a spin or orbital period associated with it, basically whether or not we can determine if the object is spinning or if it's orbiting some binary companion. We tell them what the optical source of the burst was. So if we look at the sky where the gamma ray burst originated from, what do we see there? Do we see like a supernova remnant or a distant host galaxy, something like that? And then we also tell them what the distance to that object was in light years, which is just the distance that light travels in a year in a vacuum. So in this case, it was 1.8 billion light years away. That's well in excess of the diameter of our Milky Way galaxy, which is only about like 100,000 light years. So this is a very distant object, which gives some level of indication of how energetic these objects must be if we can detect them from those vast distances. And this is just a little screenshot of the game that has been developed in association with this activity. These are the 15 different cards, and I actually might as well just leave this presentation mode real quick and just show you the game itself. So there's on the Sonoma State's Astronomy from Home webpage. You can go under Discovery and you can click the little gamma ray burst game. Anybody who wants to look at it themselves. This just goes over some of the background material that I've already told you. We teach them how to interpret, because this is intended for high school students. We don't necessarily expect them to have a lot of astronomy background. So we teach them the basics, like how to interpret distance scales in astronomy, how to interpret the electromagnetic spectrum. We give them a brief history of gamma ray astronomy and explain what's on all the cards like I just went over. Oops. And then we have the game itself. And so you can hover over each card to get a zoomed in view of it. And each one is obviously different. I will try to group them roughly correctly, and I'll make one mistake just to showcase something about the game. So let's see, this one's short. Let's see, it's a repeater. And then one thing to also point out is as I make these groupings at any given time, I can pull up this data table. This is a summary of all of the bursts. And it should basically, as I move these objects into these colored buckets, they will become highlighted on the table. So I can look at and see, are these things that I'm grouping together, do they actually share characteristics? I can basically look at all the data at once and see if the groups that I'm putting together still make sense with all the information presented at the same time. So let's see, let's repeat. Long, short, repeat, short. And these are all long, but I'm just going to have one off on its own real quick. So after all of the cards are off the table and they've been moved into their separate categories, you can click the little done button, and it'll basically evaluate how you did compared to the accepted categorization. In this case, because I moved this one over here, I didn't get the exact groupings that are currently accepted. So we get a little message saying, good job, but this grouping isn't consistent with assigned of categories, these gamma ray bursts. If you'd like to improve your groupings, press the keep playing button. Otherwise, you can press the next button to read additional information before trying again. So at any time I can click keep playing and I can move things around and do it again. Again, still the wrong answer, but I can also click the next button, and this basically just tells them information about those 3 different types of gamma ray bursts that I explained earlier. I can click keep playing with that information in mind to better understand like what these processes actually are, click done again. Oh, congratulations, you correctly sorted the gamma ray burst. Click the next button to get more information again. So, and then, so that's basically the game. And I would like to thank the people who made this project possible, including Adam Kinmont, who helped with programming web design, Aurora Simonet, who designed the gamma ray burst cards and other illustrations, and Dr. Lynn Kaminsky for general advising, as well as NASA for providing the grant which made funding this project possible. And I now have time for a few questions.
All right, seeing plenty of applause out there. That's wonderful to see. Looking for a hand up as Jesse called for questions. We'd love to have questions. Not seeing one right now. I'll ask one, which is about the activity. It ends up having a fair amount of the gamma ray burst and optical follow-up if there are. What ways in which the gravitational waves, is there plans for the LIGO, the gravitational wave component being there?
Yeah, so good question. So at the start, I mentioned how this is the masterclass is designed to be a 3-day course, and I'm contributing the gamma ray portion to that course. So there are other people working, around the world. This is an international collaboration. They are contributing the different parts of the course that will cover other parts of the electromagnetic spectrum. It'll cover neutrinos, it'll cover gravitational waves. It'll be a more complete multi-messenger course when all of that contributions have been, compiled and put together. But this is just the gamma ray portion.
Fantastic. Alex?
So I know that originally you were hoping to gather data of people who actually played this game. Are you planning on continuing this collaboration and trying to still get that participant information?
So part of this could be a question that's answered by Lynn. I know that this was also originally designed to be a 2-day activity or a 2-part activity for the gamma rays. This was the gamma ray burst sorting game, and there was going to be another one like build your own light curve sort of effect. And there's another student who's taking over that portion of it. And future students may also be able to pick up off of, getting this into the hands of students, researching, how they are interacting with it and improving upon it. So Lynn might want to add to that, but
Yeah,
that's
sure.
my general.
I'll be glad to say a couple words. So right now there's a team working on the gravitational wave part. There's another team working on the visible light observations. There's another team working on the X-ray data. And there's a team working on the neutrino data. So the idea is the students got only one of those things. And then on day 1, they learn some background, like what Jesse just did. And then on day 2, they work with the real data from the event that Jesse showed the animation of. And then on day 3, the teams with all the different messengers come together and talk to each other to try to figure out what just happened and put the data together from all the messengers, and then, hopefully conclude that it was a binary neutron star that merged, because that's what in fact happened that made the data that we're using. So that's our plan. And we're, thanks to Jesse's hard work, we're sort of ahead of most of the rest of the teams because we've now finished day 1. We'd still love to test the game on some Astronomy 100 students. So what Jesse didn't mention that he did was a whole lot of work trying to get the survey approved by the Institutional Review Board.
Yep.
And that won't be in vain, because eventually it will get approved and then we'll be able to test it out on Astronomy 100 students, but obviously not this semester. So we'll wait on that until the fall, I guess. But I am working with another student, actually not a Sonoma State student at this time, but certainly a Sonoma State student could get involved in the day 2 activities from the gamma ray point of view. So that's our next piece of this to work on here at Sonoma State.
Cool, thanks, Lynn, and great job, Jesse.
Yep.